Data labeling and annotation assign meaning to raw data so that AI systems can learn. This video explains what labeling is, why it is costly and difficult, and how annotation decisions shape what models treat as truth. Labels define the target that a model is trained to predict. Without labels, supervised learning is not possible. Labeling transforms observations into examples. It connects raw inputs to desired outputs. Unlike data collection, labeling almost always requires human judgment. Human labor makes labeling expensive, slow, and difficult to scale. Expertise requirements further increase cost. Some domains demand trained professionals rather than general annotators. In medicine, law, or finance, incorrect labels can have serious consequences. Labels are not neutral. They reflect how a task is defined and what outcomes matter. Changing label definitions changes what the model learns, even if the data stays the same. Labels can represent categories, numerical values, rankings, or probabilities. Classification labels assign discrete categories such as yes or no, spam or not spam. Regression labels assign continuous values such as price, temperature, or risk scores. In computer vision, labels may include bounding boxes, segmentation masks, or key points. Complex labels increase annotation difficulty and reduce consistency. Some labels are objective, such as sensor readings or recorded events. Many labels are subjective, relying on interpretation or judgment. Subjective tasks often produce disagreement between annotators. Disagreement does not always mean error. It can reflect genuine ambiguity. Annotation guidelines attempt to reduce ambiguity by standardizing decisions. Clear instructions improve consistency, but cannot eliminate all subjectivity. Annotator fatigue leads to declining quality over time. Time pressure increases errors, especially in repetitive tasks. Quality control is essential in large annotation efforts. One method uses multiple annotators per example to detect disagreement. Consensus labeling aggregates multiple judgments into a final label. Disagreement analysis reveals unclear instructions or difficult cases. Human-in-the-loop systems combine automation with human correction. Models assist labeling by flagging uncertain or high-impact examples. This approach improves efficiency without fully removing human oversight. Active learning prioritizes examples that are most informative to label. Better labeling strategies reduce total annotation cost. Label noise occurs when labels are incorrect or inconsistent. Noisy labels limit achievable model performance. Some models tolerate noise better than others. Label errors are difficult to detect once models are trained. Bias can be introduced during labeling through human assumptions. Cultural, social, and contextual factors influence labeling decisions. Biased labels produce biased models, even with balanced data. Documentation of labeling processes supports transparency and auditing. Label definitions should be revisited as goals change. Poor labeling cannot be fixed by more data alone. High-quality labels enable simpler and more reliable models. Labeling choices define what correctness means in an AI system. Inconsistent labels create unstable decision boundaries. Well-designed annotation improves fairness and generalization. Labeling is an ongoing process, not a one-time step. As environments change, labels may become outdated. Continuous review helps maintain relevance and accuracy. The key takeaway is that labels define the reality models learn from. Next, we explain training, validation, and test data, and why proper data splitting matters.